Hello and welcome to another video. In this video, we will see about chance constraint optimization. In the last video, we have seen optimization problem under uncertainty. The chance constraint is one approach where you can solve such kind of problems, optimization problems under uncertainty. So this on the left, you can see the problem formulation of an optimization problem that is affected by uncertainty. We are trying to find a control U such that the optimization cost f, which is a function of x, u, and z, where c is the uncertain variables and x is the state variables. So what we are trying to do is we are trying to find a control such that f is at its minimum. It has constraints subjected to equality constraints g equal to 0 and inequality constraints h greater than or equal to 0. And the initial condition is x naught. Then C belongs to a probability distribution which has mean and variance. Mean is mu and variance is sigma. Now this problem cannot be solved directly by deterministic methods because of the presence of uncertain variable. So it needs to be transferred to the problem and to an equivalent deterministic problem. It is called relaxations. So this uncertain problem is now converted to an equivalent relaxed version of deterministic problem. So how do we do that? We will consider the uncertainty as a fixed parameter in the problem. So here instead of psi, we will consider psi dash, which is most likely the mean value of the uncertainty. If the uncertainty follows some probability distribution, we can take the mean value of that uncertainty and neglect all other values. And we substitute, instead of psi as a variable, we will substitute it as a fixed parameter, psi dash, which is the mean of that uncertain parameter. Now the issue, after substituting this psi as psi dash, we can solve that same problem in a deterministic way by using deterministic methods. But the issue is that the constraint is violated by about 50% probability. So since we have the mean value, there is a chance, 50% chance that the constraint may be violated. So here that inequality constraints and the equality constraints may be violated with a probability of 50%. So that is not desirable. In some cases, it is okay to do that. So in those cases, we will proceed with considering deterministic or considering the mean value. But in other cases, it is not desirable to have 50% violation of the constraints, we will proceed with chance constraint optimization. So what are the features of chance constraint optimization? Chance constraint optimization considers probabilistic constraint. Instead of enforcing a strict deterministic constraint, chance constraint optimization ensures that constraints hold with a given probability threshold. So we will ensure that the constraints are satisfied with some probability, say 95% or 99%. So we are still taking a risk of 5% or 1% here, but still most of the time the constraint will be satisfied. By at least 95% of the time, the constraints will be satisfied. Here there is a trade-off between feasibility and optimality. By allowing a small probability of constraint violation, chance constraint optimization can achieve better objective values compared to a fully robust optimization. Here the techniques used are Monte Carlo simulation, scenario approximation, reformulation into deterministic constraints. We shall see about each one. The first and the most popular technique is Monte Carlo sampling. So suppose you have some uncertainty and it is following some distribution. So distribution of the uncertain inputs, it can be anything. See here we have considered 3 different distributions and we sampled uncertainty from that distribution. Following that distribution, we will take one sample from that distribution and run the model. So here you have some control inputs u and you have the sample psi, and this is given as an input to the model. The model is run. Model means some relationship, established a relationship between the state variables, control variables, and where the uncertainty is affecting. So that relation is the model. So model maybe first principle models or some kind of mathematical relations that is established between the state variables and the control and uncertain variables. So now the model is run for the particular sample and the corresponding output state variable is got. So similarly, we run that many times. So this sampling is done many times. For each sample, we will run the model and get corresponding state variable. Now we will get a output probability distribution for the corresponding state variables. So there is now a relation between the input variable and the output variable. Now the advantage of using the Monte Carlo simulation is that we can consider any kind of input distribution. The input distribution can be anything. Still this method will work. So we need to sample from that corresponding distribution and run the model to get an output distribution. Monte Carlo simulation is a of many of the chance constraint optimization problem, and it is a very popular technique of scenario approximation. Converting a probabilistic constraint into a deterministic tractable form using a finite set of sampled scenarios. Here, there is a limitation that requires many scenarios for high confidence. More and more scenarios will give you more confidence. So this will but increase computational cost. And there is no strict guarantee of feasibility for unobserved realizations. So only the realizations which we consider as scenarios, for those realizations we can guarantee feasibility. For other cases, for other unobserved realizations, we may not be able to strictly guarantee feasibility. It can be conservative if we consider too many scenarios. If the number of scenarios is too large, then the solution that we get may be conservative. Here the optimization problem is minimization, minimize f of x, where x is our decision variables subject to inequality constraint. Now inequality constraint is a function of the state x and the uncertain variable psi. Now psi S is nothing but different scenarios where S varies from 1 to n. If we consider n different scenarios, we will have psi 1 to psi n. Now, so the number of constraints increases as we consider more and more scenarios. But this method is very popular. Scenario-based approximation is very popular among chance constraint optimization. Reformulation of the optimization problem. Suppose an objective function f of x is minimized subject to this constraints. The first approach is scenario-based approach where we sample each scenario and then consider that in the optimization problem. The other case is a robust case where we the maximum value of the uncertain parameter in the constraint and then run the optimization problem. So here in the second case, in the robust case, we consider only one constraint. But that constraint is a very conservative constraint since we are considering the worst case scenario. Now solution approaches for chance constraint optimization. So here exact methods and approximation methods are used. The exact methods we reformulation using the probability distribution. Suppose we know that the uncertain parameter follows some distribution. We use the information of that distribution such as mean, variance, second moment. All those informations can be used to reformulate our constraint into a deterministic constraint. So that is a basic primary approach for solving chance constraint optimization or optimization problem which is affected by disturbance, uncertainty. Now deterministic equivalence for special cases. If the problem itself has some special features that can be used to convert the constraint into deterministic fashion. Approximation method might use Monte Carlo sampling where you take a large number of samples and run the model to get corresponding output and then determine how the constraints can be modified. Scenario-based approach, on the other hand, where we take samples and then we consider more and more scenarios or more and more constraints corresponding to each sample that we are taking. So that is another approximation method. So how this is developed? The first block shows our general optimization problem where we are trying to maximize or minimize f of x, which is our objective function, subjected to equality constraint and inequality constraint. Equality constraint gi of x equal to 0 and inequality constraints hj of x less than or equal to 0. And this decision variable will be within a set x. Now here our primary focus is on that inequality constraint hj x psi, because now the state variables are affected by uncertainty psi. Now that is now written in probabilistic fashion, meaning probability of satisfying this constraint hj x psi less than or equal to 0 is greater than alpha. So by 90% probability, we can say that this constraint is satisfied, or by 95% probability, we can say that the constraint is satisfied. Based on our requirement of alpha, we can say that the probability of satisfying the constraint is greater than or equal to that alpha value. It is true that we are taking some risk. So beyond alpha, beyond say 90%, that 10%, it may not be satisfied. There may be violations in constraint. So that risk, but in most cases, most scenarios, most alpha value, so 90% chance that the constraint is satisfied. Challenges and limitations of considering this chance constraint optimization. The computational complexity increases for large-scale problems. As we consider more and more scenarios, as we consider more and more samples, the problem itself becomes computationally expensive. And this becomes more complicated when we consider nonlinearity in the general probabilistic constraint. In some approaches, there is a need for accurate probability distribution of the uncertainty. Only then we will be able to reformulate. Only then we will be able to accurately calculate for this particular alpha value, for this particular probability, the constraint will be satisfied. Ultimately, we are having a trade-off between robustness and optimality. These are the future directions of chance constraint optimization. Chance constraint optimization is being implemented in the real world more and more. So this brings in new challenges. So theoretically, some optimization routine may work, but a practical implementation will bring out more issues associated with that theoretical approach. Now people are implementing more and more in various domains this chance constraint optimization. Growing use of artificial intelligence driven optimization and real-time control. Now artificial intelligence learns about that uncertain parameter. It is suitably, it can model that uncertainty, the probability distribution, and that can be used in the optimization. It can also be used in the time control, like the present value can be measured and then used it in the optimization, used it to update the constraints in the optimization. Something like a model predictive control framework. Data-driven chance constraints using machine learning is one of the future directions of this chance constraint optimization. So we will see more about chance constraint optimization in the next videos. Thank you.